Okay, I think I'm finally ready. Okay, so a null hypothesis is always that a population mean equals something. So we're saying, is the current population mean for these homes the same as it was before? That's what we're saying. And then in the test, can we conclude, yes, the population mean is 243,785? Will we conclude that in the test? Can we conclude that in the test? She says no. No, we never. Our conclusion in a hypothesis test is never that the null hypothesis is correct. That can't be a conclusion. Instead, what would the conclusion be? Right. Do you see? We don't reject it. We say it could be true, or there's not enough evidence to say that it's not true. It very well could be true. That's the best we can do with these. So the hypothesis is that the population mean is a certain value, but we can never prove that with the evidence. We can only say there's not enough evidence to refute that. Okay? So a type 1 error, so this is asking about type 1 and type 2 errors. A type 1 error would say that, what? So without looking at the answers, because it's too long to take, do we just remember? We just have to remember what a type 1 and type 2 error, because there's nothing in the phrase type 1 or type 2 that gives us an indication of what it is. We just have to memorize it. What is a type 1 error? Who remembers? Yeah, Joey. Yeah, right, exactly. So we rejected it, and it was true. Or we shouldn't have rejected it. Okay, so let's read these now. Which one of those is this? Type 1 error would occur if in fact it's true, but the results of sampling lead to a conclusion that it's less. Is that what he said? Sounds like that's what he said, but let's read the other ones just to make sure. Type 1 error would occur if it's less than, but the sampling led to us to conclude, what's B? That's type 2. A type 1 error would include if in fact, but the results of sampling failed to lead to the conclusion that. So that's saying the same thing twice, right? It's in fact this hypothesized mean, and the results of the sampling failed to lead us to the alternate. Well, that's kind of saying the same thing twice, right? It's got to be A, right? So this is our type 1 error. The hypothesized mean is correct, and we reject it instead just because of the data we had. Is that done? Okay, so you only had probably one chance at that. So is there? All right, maybe there's more. There it is. Type 2 error. Type 2 error we said was B, right? So type 2 error is that we rejected, but the data, the data led us to conclude what? To not reject, but we should have rejected, right? A type 2 error would occur if in fact the sampling, the hypothesized mean is less, but the results, our evidence, led us which one of these? Oh, fail to. Fails. Okay, so yeah, so I just didn't read cleverly. So the type 2 error would occur if in fact we should reject, right? But the results of the sampling fail to lead us to that conclusion. And we didn't reject. It's this one. Correct decision. Correct decision would occur if the mean is this, and the result lead us to the rejection of that fact. Is that a correct decision? No, clearly not, right? Correct decision would occur if mu is not. Is this the hypothesis test we're doing? No. No, we're doing a left-tailed test, right? So I'm guessing this is a two-tailed test. Correct decision would occur if, and the results of the sampling do not lead us to reject that fact. or if the mean is less and the results lead us to that conclusion. This is kind of like common sense. It's kind of like you can almost get this right without having done it before, right? Just by reading carefully. Questions on this one? Type 1 and type 2 errors. Questions on that? It's on the test. Okay, we want to do number 8 next. Okay, so here's an actual test that we're going to do. Okay, sample mean, sample size, population, standard deviation are provided below. Use the one mean z-test to perform the required hypothesis test at the 10% significance level. So let's make sense of what we're given here. What is x bar equals 23? What does that mean? X bar equals 23.
That would be the sample mean.
She's saying that's the sample mean. Agree with that? Yep, so we took some sample. How big was our sample? We took 35 observations in some population, and we took the mean of those, and we got a mean of 23, an average of 23. Okay? So, and then this is, and what is the sigma equals 7? Of the population or of the sample? Population or sample? Important, we got to know this. She says population. Agree? That's population. Population standard deviation, which means we're going to use what kind of test? Because on the exam, you're going to have to decide if you're going to use the z-test or the t hypothesis test. So if you're given, if you know the population standard deviation, like in this problem, z or t? Z. Okay. If you're given the sample standard deviation, that's when you use the t-test. And what's the symbol we use for the sample standard deviation? They're saying S, right? S for sample standard deviation. You can think of it that way. Okay? And this, maybe the sigma kind of looks like a flipped over and flipped around P. So just some kind of mnemonic device. Kind of looks like a P if you flip it and reflect it a little bit. And then S for sample standard deviation. Okay? All right. So we're going to use the z-test, and if we were just, if we didn't have the, if we weren't doing the hypothesis test, what would be our point estimate for the population mean? What would be our point estimate for the population mean? So here's the information we have from our sample and from the population standard deviation. And we're going to say, this is our best guess at the mean of the population. What is it? He wants 23. Yeah, the sample mean. The sample mean. Okay? So if that's what we call a point estimate of the population mean is the sample mean. That's all we've got, right? It's all we've got. We wouldn't know anything otherwise. But now with a hypothesis test, we have some kind of other information, and we're saying we're going to check to see if the mean is, in this case, we're going to check to see if the mean is 25 or if it's less than 25. So that's what the hypothesis test is about. We've got the sample information, but we want to test to see if the population mean is 25 or the alternative, it's less than 25. Okay, so the test statistic is the z value for what? For our sample. The test statistic is the z value for our evidence from our sample. So how do we get z? So we're going to do 23, right, minus 25 over 7 Divide by the square root of 35. Done this a lot, right? So we use the sampling distribution z-score, right? The sampling distribution z-score for the sample size of 35. Okay, who's got a calculator? Crank it out. Negative 0, negative 1?
Negative 1.69.
Negative 1.69. Okay, that's our test statistic. It's the z-score according to the sample that we took. All right, and so if we want to make a picture of what's going on here, here's our distribution. What is going to be the mean in the picture? 23 or 25? Our hypothesized mean. Hypothesized mean, 25, which is a z-score of what? What's a z-score at the mean? 0. Okay, so this would be like our x-bar distribution, and then this would be our z-scores. So we can write them both on the same picture. Okay, and what do we have? So we're checking out 23, and we got a z-score of? Okay, so, and now we have to figure out, so they said 2 decimal places. Is that rounded correctly, the negative 1.69? Great. Okay, so we need critical values. So the critical value, first of all, is it going to be two-tailed? So we didn't really see this before. So basically they're saying, is it two-tailed, or is it going to be, this would be right-tailed because your z will be positive, or will it be left-tailed where we're going to have a negative z value? So we look at our alternative hypothesis. Two-tailed, left-tailed, or right-tailed? Left-tailed. Okay, so we're going to choose this one, first of all, and now we need to put in what our critical value is. And our critical value comes from what? The fact that we're using the 10% significance level and a z-test. All right, so our critical value is going to be determined by using a 10% significance level. Okay, so if it's a left-tailed test, then how much area is going to be there? We're just doing a left-tailed test at a significance level of 10%. How much area is going to be what I've shaded? No, how much area? How much area? That's, you're thinking z-score. How much area will that be? What's that? You're just thinking z-scores also.
Oh, yeah.
10% of the area, right? 0.10. Right? Okay. 10% significance level is the probability of making a type 1 error. And probability is the same as, or percentage, same as area under the curve. Right? That's alpha equals 10%. That's the probability of making a type 1 error. Probability is the same as the percentage of the time that you'd make an error. And remember, our percentage is area under the curve, right? So 0.1. So now we get our critical value. Critical value is the z-score that has 10% to the left. And what is that? You got 1.282. Somebody else get that from your chart? What? That's if it's 5%. Yeah, I think that's if it's two-tailed. You need a 5% would be 1.96. So 1.28 then?
Yeah.
Okay, so here's the thing. No, so they're saying the opposite of z. So what is, oh, let's see. This is really a weird way to ask this question. Okay. So it is negative. It is negative. Okay. So let's draw the picture. So here we are at 1.69. And where's negative 1 point, or yeah, negative, and where's negative 1.28? It's like here, right? So this is our critical value. So this is our non-reject region, right? Non-reject. And this is our reject. And our z-score is negative 1.69. So do we reject or not reject?
Reject.
We're going to reject because our test statistic is in the rejection region. It lies here. Here's our rejection region. Our test statistic of negative 1.69 falls in the rejection region. So we're going to reject. Reject the null hypothesis, the data. So first of all, we're testing to see if the data, the mean is okay, so for rejecting the null hypothesis, that means the evidence did tell us something, right? It means the evidence do provide, right, sufficient evidence to conclude that the mean is less than 25, okay? So rejecting the null means that there is sufficient evidence to say something. So that's what you got to get this one right to get this one right. So you have to, if you say do not provide, then that's like when we don't reject, right? When we don't reject, that means there's not enough evidence. So if we're rejecting the null, that means there is enough evidence to say something, and that is that we go with the alternative hypothesis. So there is enough evidence to conclude that the mean is less than 25. Okay, questions on this example? All right, so let's talk about p-values. P-values are important. I don't know how much practice you got in this homework with p-values, but it's on the test. So let's talk about p-values. What is the p-value for what we got? Negative 1.69. So we got a test statistic of negative 1.69. What's the corresponding p-value? Remember that p-value. So the p-value is the percentage or probability or significance level associated with what we actually got from the sample, not from the critical value. So we're going to look at this negative 1.69 and we want to ask, okay, what's the p-value for a z-score of negative 1.69? So remember how to do this? You go to your table and you're going to do a z-score of negative 1.69, and now we're interested in what? That area to the left of 23, which I've shaded in black. Okay, so is it going to be more or less than 10%? Is it going to be more or less than 10%? Less. It's less area, right? It's going to be less than 10%. Anyone got it? So our p-value, so our test statistic was negative 1.69, gives a p-value of what? 4.55%, or 0.0455. So if we were making our decision about rejecting or not rejecting, we know that the significance level was 10% or 0.1. So when do we reject based on a p-value? When do we reject based on a p-value? When the p-value is less than alpha, or when the p-value is greater than alpha? Less or greater? What's our alpha in this case? 10%. It's all the red shaded area. When are we going to reject? When we have less shaded area or more? Less, right? We're going to reject when our test statistics gives us less shaded area or a p-value that's less than the significance level. So this is maybe we haven't talked about this before explicitly, but it's important. Reject the null if p is less than alpha. We rejected because we were in the negative 1.69 was to the left of negative 1.28, and that results in less area than the area indicated by our significance level. Like 4.55% versus 10%. Okay, does that make sense? Does that make sense? So the p-value is it's the area or associated with our actual test statistic as opposed to the critical value, right? And so what would you compare a p-value to? You compare it to alpha, right? Because those are both percentages or both areas. And if the p-value is less than alpha, you reject the null. If the p-value is not less than alpha, you would not reject the null. So if our test statistic was over here, then we'd have a p-value bigger than the rejection region, and we wouldn't have rejected. Okay, questions on that? All right, what next? So we got 13 and 17?
Yeah.
All right, that's really similar to the one we just did. Oh, but except it's a t-test. Okay, let's look at 17. Let's look at 17. Just pick one of these two. Let's try one of these because let's do this last one. Because it's a t-test, and then also it's we have to make sense of a real-world situation, which is the whole test is like this. Okay, the whole exam is like this. Okay, so we got this Abi Index compares the blood pressure of a patient's arm to the blood pressure in their leg. A healthy ABI is 0.9 or greater. In a study, researchers obtained an ABI of 186 women with arterial disease. So let's talk about the 187. What's this number mean? Sample size, good, sample size. So sample size is n equals 187. So this is really a good skill to have here. Rather than just trying to jump in and solve the problem, let's write down the important information and what it means. It's our sample size. The results were a mean ABI of 0.9 with a standard deviation of 0.13. It's kind of a trivial question, isn't it? So they're saying that the results were 0.9. So what symbol is that? So what are we gonna What is that? That's 0.9. Sample mean. It's the results. Results meaning from our sample, we got 0.9. Is that? With a standard deviation of 0.13. And so, yeah, so it's implying a sample standard deviation. It doesn't say population standard deviation. You also, they give you a big clue here too, because they're telling you it's a t-test. So our sample standard deviation is 0.13. And so a healthy point ABI is 0.9 or greater. I'm kind of scratching my head. Did you guys you have different results of your, like, did you have a different result of your sample mean? 0.9 and 0.9 it was the same? Okay, I guess we can still do it, but do we need to do it? What, so do you understand what's happening here? They're testing to see if the healthy ABI is 0.9 or if it's greater than 0.9. And then we got a sample mean of what? So are we going to reject the null hypothesis? Of course not. We got the mean. The sample mean is our hypothesized mean. So we would never reject it because that's basically what we're estimating the mean to be. So that's the kind of thing, hopefully, that you, before you start the problem, you come to conclusions like that, so, because you understand what's going on. So if our mean of our sample is the same as the hypothesized mean, then we would never reject. It doesn't matter what the standard deviation is or the size of our sample, we wouldn't reject. So let's say that, let's do something more interesting. So let's say we got 1.05. So, but I bet you probably want to still go through the problem for the right answers. Is that correct? So let's go through it anyway, and then we'll see if it makes sense to change it. Okay, 10% significance level. And are we doing a left-tailed, right-tailed, or two-tailed test? Left-tailed, right-tailed, or two-tailed? Based on what's given, the information in the problem. A healthy ABI is 0.9 or greater. So what is an unhealthy? Yeah, so unhealthy would be what? Less than 0.9. So what kind of, is this left? This is a left-tailed test. So unhealthy would be not healthy. So it'd be less than 0.9. So the null hypothesis is, the null is always, always, always that the population mean equals something. Okay? For us, equals 0.9, right? And so then our alternative hypothesis is unhealthy, less than 0.9. Okay, test statistic. So we have the 10%, so we're doing this thing. So T for 10%. So you're going to go in your table, and the table, what is the picture? You got to look at that picture in that table. Is it, we might have to do a little subtracting here. So the picture in the table, is it, are all the t values up here? I forgot what that table looks like. Okay, so we're just going to do the opposite of what. So we're going to use 10% was how many degrees of freedom? But I don't think your table goes that high. It just gives you at the bottom of the table, it just gives you what number to choose if it's greater than what? How many? What's the maximum degrees of freedom in your table? Hi. Who are you? Who are you? You're not in this class, are you? Okay. All right. And so what's the maximum degrees of freedom? The 49. So then anything greater than that, you just use the same value. So for 10%, and we don't have to split it in half because it's just a one-tailed test. So alpha is 0.10, and we just take that number that's for anything greater than 50, and what do you get? What is that? 1.282. All right, but what's this going to be for a left-tailed test? Negative, right? So our T alpha is negative 1.28. Sound familiar? Isn't it the same number we had for the last problem? Why is it the same number that we had for the last problem? At 10% significance level. What? But this isn't. It's. Why is it the same as the z-score? I thought it was supposed to be different because we only had the sample standard deviation. There's a reason.
I remember doing this on the homework, and I think that gives you the graph right there where it says click to view the partial table. It gave me a different number.
Oh, this isn't negative 1.28?
Like if you click on the graph,
then it
gives you like what it is for 100.
Oh, thank you. All right, cool. Oh, look at that. So, yeah. So if you used negative 1.282, so what is it? Where are we? 100 and what?
186 would be 1.286,
Negative
negative 1.286.
1.29. So negative 1.29 if we're rounding. So if it's in between these two and we're rounding to 2 decimal places, it's the same, right? Negative 1.29. That's not the test statistic, though. That's the critical value. That's the critical value that we were doing. Were you thinking that? He's doing the wrong thing. Were you thinking that? You should have. Right? I make mistakes too. All right? I do. I make mistakes. And if you were thinking, no, he's doing the critical value. He's not doing the test statistic. Speak up, okay? All right, so they're asking for the test statistic. That's what? That's the number, the t-score that's going to come from our sample, right? So t is going to be 0, right? Because it's going to be the 0.9 minus the 0.9 divided by s over square root of n. But that doesn't matter because it's just 0. Now it's going to ask for the critical value. We already did that work. So what's the critical value? It's going to be a left-tailed test. So it's going to be this thing. So this is 3 decimal places. So negative 1.286. Fantastic. Okay. So and now this is what we knew all along. Reject or do not reject? Yeah, our sample mean was the same as the hypothesized mean. So that's our estimate for the mean. So we would never reject it, right? We would never reject it. Makes common sense, right? So don't reject it. All right, so the data provide or do not provide? When we don't reject, we're saying not enough evidence. Not enough evidence to conclude otherwise. Unhealthy. Too low, right? Unhealthy. Too low. Okay. Oh, let's not do the p-value for t-test. All right, so p-value will only consider for a z-test, not a t-test. All right, let's do some more examples. We've got pretend we're taking the test. Let's see if we can do these. To the left of z of 4.66. So what's the biggest one you have? Negative 3.9, which is?
Zero.
So what's going to be a negative 4?
Zero.
0.
Okay. Okay.
Okay, which one should I do? We're running out of time. Which one of these should? Okay, someone has nominated the second one. Is that what you want? Second one? Okay, I'll do the second one. Ready? Here we go. Okay, here we go. So the average period of all seals, lactation nursing period for all seals is 23 days. What is that? So we look at that. What is that? Population mean. We got to recognize that's a population mean, 23 days. Okay? And that's actually going to be should have came up with, that's the null hypothesis for this. And the alternative is, it says, does data provide sufficient evidence to conclude that the mean lactation period of gray seals differs from 23? Alternative is? Does not equal. It's a two-tailed test. Okay, so your priority should be you're engaging here as getting ready for the test, not writing down what I wrote on the screen to get the points. Okay, we're trying to get ready for the test. So get your mind in that mode, whatever it takes. Okay, so the alternative hypothesis is? Yeah, because the test is worth far, far, far more points than this one problem on this blue sheet. Okay, so not 23. Okay, good so far. So then it says a sample of 14 gray female seals. What is that telling us right there? Sample size. And then they told us that the sum is 274.9 days, which helps us get the sample mean. So it's that sum, 274.9 divided by 14. Madison, tell me. 19.64 days. And they gave us a population standard deviation of 3. Is that S or sigma? And are we going to do a z-test or a t-test? Z-test, because we have the population standard deviation, z-test. Okay, so we want to get the test statistic and critical value. So the test statistic comes from the sample, and that is our z-score of 19.64. Minus 23 over 3 divided by square root of 14. Agree? So that's the z-score that for the sampling distribution that the sample is indicating. Tell me this number. Negative 4.19. Somebody else get that?
No, I got negative 4.26.
It's not going to matter. So negative 4.19 and negative 4.26 are going to be the same thing anyway. But are we negative 4.19? Are we good on that? Okay. All right. Okay. So I think if you don't round ahead of time, this is what you get. Okay. So that's our test statistic. That's what the sample is indicating. And we're going to compare that to the critical value, which is also a z-score, which we get from what? The significance level. The significance level of 5% of a two-tailed test means you're going to look at what area under the curve? Yeah, if it's a 5% significance level on a two-tailed test, half of your area is going to be on the left and half is going to be on the right. So that's 2.5%. Or you're going to look for 0.025. So either you have to, so you have to think about this. You're going to look at positive, what? So for an area to the left, you're either going to look at positive 0.975, right? Either a positive area of 0.975, or you could go over to the left side of the table and look at negative 0.025 will give you the same thing. Does that make sense? I shouldn't have put that there. But for 2.5% on either side and a table that gives you areas to the left, that means you're going to look for an area of positive 0.975. That'll give you the right positive z-score. Or an area to the left of so it's still positive, but it's in the left side of the table, so it's still positive, not negative. So one of those two. So what did you get for a z-score? Yeah, we've done that before, right? Plus or minus 1.96. Okay, so let's make our picture. Okay, not the best normal curve I've drawn today. All right, so we're saying that the rejection region, or the non-reject region, is between negative 1.96 and 1.96, because this is how much area right here. And this is how much area right here. How much area is that? 2.5%, or 0.025. And so similar, that is 0.025. Okay? And so what do we get for a z-score? Negative 4.19. Is that in the non-reject region or the reject region? Way out here. It's like not even close, right? It's way out here. Negative 4.99. Or 19, sorry, thank you. 19. All right, so what's the conclusion of the test? We're going to do the p-value too. What's the conclusion of the test? Reject the null hypothesis. And what's our interpretive statement? There is or not, right? There is sufficient evidence to say that the mean is not equal to 23 days. The evidence is saying it's way lower than 23, right? Because we're way over here. So now the p-value. The p-value then is the area, this area over here, to the left of negative 4.19 for z-score. That's going to be the p-value. Comparing to what? And what are we comparing it to? That p-value would be compared to the area, that area, we compare it to this area, the black area, which would be starting here all the way to infinity, like this. And so the p-value, you're going to compare to 0.025. You're going to compare the p-value to 0.025. If the p-value is greater than 0.025, would we reject or not reject? Not reject. If you get an area greater, that means that the z-score was here, and we got a bigger value. So if that was a bigger area than 0.025, we would not reject, because we'd be here. If you get an area smaller, if your p-value is smaller than alpha over 2, and in this case, for this right here, you're going to get a p-value of 0. Because the lowest z-score on there is what, negative 3.9, and we're to the left of that. So at negative 3.9, they're calling it 0. So we're even further. So there's virtually 0 area here. And since that amount of area is less than 0.025, that's also a way to say that we reject the null. The p-value 0 is less than alpha over 2, our 0.025 number. So there's kind of two ways to do the test. You compare the test statistic to the critical value, or you can compare the p-value to the significance level, alpha. You got to know the p-value stuff.